The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon. Thank you everyone so much for attending our European webinar. Today we'll focus on the viscosity of pharmaceuticals. We'll introduce viscosity measurements with Riosense's VROC Initium 1+. I'd like to introduce Dr. Zachary Imam, who will be going ahead and giving the presentation.
Hello, welcome to today's webinar. I'm Zach Imam. I'm a research scientist here at Riosense in California, and today I'll be sharing with you our presentation on viscosity and pharmaceuticals, introducing you all to viscosity measurements with the VROC Initium 1+. So to kick things off, we'll go into a basic overview of what viscosity is. Viscosity is the resistance to flow by a fluid. It's the ratio between the shear stress experienced by a fluid divided by the shear rate experienced by a fluid, or deformation rate. And this shear rate is a velocity gradient that is perpendicular to the direction of flow. So in this diagram, fluid is moving from left to right, and the shear rate is changing perpendicular to this direction. So in this example, it's the parallel plate geometry. So this bottom plate is stationary. This plate is moving at a velocity u plate, and the velocity is going from 0 down here to the velocity of the plate, and this forms a gradient where the different fluid elements are shearing or sliding past each other from bottom to top. And so we could say that this viscosity, the viscosity of the fluid is the molecular friction between the molecules within the fluid as they are resisting flow by this force applied by this plate. And so this response of the fluid reflects its molecular level behavior and structure. So like if your fluid has particles inside, what is their size? How big are they? What is their shape? Are they proteins that dimerize or oligomerize in some form or fashion? Are these electrostatically interactive materials? All of these behaviors are reflected in the viscosity, as well as any possible microstructure between different components within the fluid. So in an ideal world, we could shrink ourselves down and observe these things happening in real time. However, we can't do that. So we need to probe our fluid's response in order to get a gauge for these kinds of behaviors within the fluid. So we can think of the viscosity as a fluid's response to this deformation, and it changes based on what's actually inside your fluid. So if you have a protein formulation, it's going to tell you a little bit about how your proteins interact with each other, how they interact with the different excipients in your formulation, as well as any size or shapes that they may take once in solution. So with that in mind, we're going to talk a little bit about our technology, VROC Technology, viscometer rheometer on a chip, which is a combination of microfluidics and MIMS, so microelectromechanical systems, where we have a flow channel, where we have 4 pressure sensors aligned linearly in this rectangular flow channel. So that is important, this rectangular flow channel. We know the cross-sectional area, the geometry of this flow channel, which will allow us to calculate the shear rate that our fluid experiences while it's in the channel. And so we have these 4 pressure sensors, and they each read a pressure as the fluid is flowing through the channel. So we have pressure-driven flow. On our system, we control the rate at which the fluid flows in our channel. So we control the flow rate Q, which, since we know the geometry of our channel, we can calculate the shear rate from that specific flow rate. And then we measure the pressure drop across the 4 pressure sensors. We know the pressure at each sensor that each sensor is reading, and we know the position of each sensor. So we get a derivative of the change in pressure as a function of distance along the channel. And this derivative, we can then, again, knowing the dimensions of the channel, we can then calculate the shear stress. So then we can just divide shear stress by shear rate to get the dynamic viscosity of our fluid. So we can control shear rate and then measure shear stress and then calculate viscosity. So every rheometer on the market has to calculate viscosity. They have 1 or 2 ways of doing that. They either control the shear stress and then measure the shear rate and then calculate the viscosity, or they do what we do where they control the shear rate and then measure the shear stress and then calculate the viscosity. So every instrument calculates viscosity. It's a calculated property, but you need to control one or the other and then measure, and then you can use those parameters to calculate viscosity. So next, our product, the initium, VROC Initium 1 Plus. It is our high throughput automated viscometer, rheometer. So the absolute minimum volume you can use to get a number for viscosity is 26 microliters. However, if you want the full range, the full capabilities of the instrument, 50 microliters is minimum. It comes in 2 different orientations with a 40 vial rack setup or a 96 well plate setup. The initium has this ability to retrieve your sample. So once it goes into the channel or into the flow channel and it uses all the volume that was loaded into the test syringe, it can then pull back and then remeasure that sample. And it can do that to infinity and beyond. So you can get tons of data with the VROC Initium. And because this ability to retrieve the sample back into the test syringe, we can actually recover the sample and put it back into the vial rack. And then you can take your sample and use it to perform any other characterization experiments that you would like to do, or you can make it a destructive test and not worry about recovering your sample. The chip has a temperature range between 4 and 70 degrees Celsius, while the vial rack has a temperature control range from 4 to 40 degrees Celsius. You can perform rate sweeps, shear rate sweeps, and temperature sweeps, and it has even more customizable measurement protocols, and then it has a variety of different cleaning protocols. With another cool feature of the Initium 1 Plus that is an improvement of our old instrumentation is it's compatible now with organic solvents. So if you have formulations that are suspended in, like, say, chloroform or toluene or something like that, you can use those solvents on the 1 Plus as well. It's much more efficient at cleaning than our older models, and it uses smaller volumes of all the cleaning solvents, so it's much more efficient in its cleaning. And it also has features where you can select what cleaning solvent you have, as well as what chip type you have, and it helps prevent any confusion when trying to build experiments, so you don't accidentally pick the wrong cleaning protocol based on what chip you're using. And then some more background on the 1 Plus, as you can see on the top here. This is actually a screenshot of our older instrument, but it's functionally identical to the 1 Plus. All additions are there to improve its cleaning capabilities, as well as making it more compatible with those organic solvents. But the process by which it measures the viscosity is the exact same. So we have our test syringe here to 100 microliters. You then push the sample through here into the chip where it measures through that pressure sensor array, and then it can pull back and then remeasure and then pull back and then remeasure over and over again as many times as you wish. And then once everything is done, you can either pull back again and then deposit the sample back into the vial, which is again called recovery, or you can push the sample all the way through into the waste port here, and then the instrument cleans itself. So with that background in mind, I'll just quickly go over what we'll talk about today. We'll talk about the benefits of measuring viscosity from sample injectability and processing. We can predict performance and processability with viscosity. Like I mentioned before, it reflects the microscopic behavior, including the individual molecule size and shape, its interactions, if it forms any complex structures, how the environment impacts all of the above. We like to tell people this is intelligent formulation. Work smart, not hard. So you can use these viscosity measurements to kind of predict how your sample will behave in different environments. And so you can get an idea of what it will behave like when you change your formulation, when you're optimizing your formulation. So with that all in mind, I'll talk a little bit about the sample recovery feature, how we can measure the sample, and once we're done measuring, we can then put the sample back into a vial so then you can use it for other experiments. Talk about injectability of concentrated protein solutions, its storage stability with sample age, temperature variation of concentrated proteins, and then how your excipients and your proteins change how the viscosity behaves at different shear rates. So with sample recovery, what we have here is on the x-axis, we have the sample volume that we input into the instrument, and on the y-axis, we have the efficiency of recovery. So how much sample did we recover based on the sample volume we initially input into the instrument. And then we also have this monitored or differed by different viscosities. So we have 3 centipoise, 10, 50, and 150 centipoise. And centipoise corresponds to millipascal seconds. They're the same unit, it's just different notation. They mean the same thing. So 3 centipoise is a low viscosity fluid, and 150 centipoise is a high viscosity fluid. And so as you can see here, the efficiency at which you can recover your sample is directly dictated by the sample volume and the viscosity of the sample. So high initial volume, low viscosity, you have the most efficiency. And then low volume, low viscosity, you have about 40% efficiency. So if you input 26 microliters, you're only going to get 40% of that back when you hit recovery if you have a high viscosity sample. So whereas at 100 microliters, you'll be able to get about 70% of that high viscosity fluid back. So these are a couple features as well. Also, we can then monitor, does sample recovery change the viscosity in any way, shape, or form? And the answer is no. So we have in dark blue the initial viscosity reading, and then the next lighter blue is an experiment after 1 recovery, experiment after 2 recoveries, experiment after 3 recoveries of the same sample. And as you can see, the viscosity remains constant throughout. Doesn't matter if you're using eye drops or you have bovine gamma globulin or bovine serum albumin, and also with just a standard buffer, phosphate buffered saline, you get the same viscosity no matter how many times you recover the sample. So, yeah. So then with concentrated protein solutions and their storage stability, here we got 2 different types of bovine gamma globulin powders, one labeled premium, one labeled elite. Difference between the two was that the elite had a certificate of analysis with a microbial analysis conducted, so that basically we know that in the elite form, this is all bovine gamma globulin, very little contaminants, whereas the premium doesn't get that distinction. So looks like it's actually a little bit different, 2.35 centipoise versus 2.45 centipoise at 100 mg per mil in PBS. And we stored them at 4 degrees Celsius and then waited for, we measured them every day, and then after 2 weeks, and then after about a month to about a month and a half, 6 weeks, to see how the viscosity changed with age, to really monitor how stable are these protein solutions at refrigeration temperatures. It's like they're pretty stable after about 14 days. However, past 14 days, that's when they start to change their viscosity noticeably. And we can even demonstrate this percent change in viscosity. So it's less than 1% different after 2 weeks, but then 2 and 3% respectively for the premium and elite after a month. And then after 6 weeks, it's 6.5 to almost 10% different between the premium and the elite. And, we can kind of infer some things about our solution. One, it's fairly stable after 2 weeks, and it begins to start showing signs of aging after a month at refrigeration temperatures. But we also can see that for whatever reason, the elite, and maybe because it's more pure, the elite is more sensitive to age-related changes. So in relation to the premium formulation. So there may be some benefit to the extra components in the premium formulation that prevent it from aging as dramatically. However, they still track at the same time frame. They age at essentially the same points. It's just one's aging is more dramatic than the other. So still focusing on aging, looking at storage stability. So in this example, we have 250 milligram per milliliter bovine gamma globulin formulations in PBS with excess sodium chloride, PBS with arginine included, and then PBS with arginine and excess sodium chloride. And again, these were stored at 4 degrees Celsius, and we measured their viscosity at 25 degrees Celsius over time. And the different colored bars indicate different time points. So black is day 1, red is 7 days, blue is 14, gold is 28, and then green is 55 days, and then 92, which the arginine formulations got to, are in yellow. And the reason why there's still data at 92 days for these arginine formulations and not these base formulations is that the proteins flocculated or crashed out of solution and formed crystals in the PBS and excess NaCl PBS formulations, indicating that arginine not only increased their time in solution regards of aging, but also prevented flocculation or crashing out of solution to occur at accelerated aging. So we can kind of see that a common excipient used to reduce the viscosity of formulations, arginine, also helped prevent any age-related changes to the formulation, which is an interesting finding. And again, this is something you can do with viscosity. You can kind of see, we believe arginine reduces electrostatic interactions between proteins in solution. This reduction in interactions can help increase their shelf life, their storage time, as well as reduce their viscosity. And lo and behold, not only did the arginine reduce the viscosity noticeably, as you can see in the black here, it also delayed the onset of changes related to aging, and even formulation that include excess NaCl, which aged very poorly at 55 days and was the first formulation to flocculate. So next, temperature sweeps with concentrated protein solutions. So again, 250 mg per mil of bovine gamma globulin in PBS. We looked at pretty relevant temperatures, storage and processing temperature at 4 degrees Celsius, delivery temperature at 25 degrees Celsius, and then body temperature at 37 degrees Celsius. And so we can predict what the viscosity will behave like for our buffer formulation, which is here in red, demonstrating what we expect the buffer to behave like at different points of temperature. However, when we actually measure our protein formulation at these relevant temperatures, we notice they deviate dramatically from the buffer, which indicates that, again, the proteins themselves, the molecules in solution, are reacting to the shear stresses we input when we're measuring viscosity or using these protein formulations. So this concentrated protein solution is 430 centipoise at 4 degrees Celsius. Really, really, really viscous fluid. And so that would be kind of challenging to flow. You need a large amount of energy to induce that formulation to flow quickly, like in a processing environment. And if you were to use the formulation without letting it warm up to room temperature, you're going to experience more viscous fluid than if you say you wait till it's time to use at 25C, where it behaves at 82 centipoise, and then it even decreases in viscosity further at the higher temperature. It's 10 times more viscous at 4 Celsius than it is at 37 Celsius. That's a major difference, an order of magnitude. And so we can also use temperature to determine the activation energy of protein solutions. It can vary with concentration and interactions. It can change with the different buffer formulations that you use. However, do note that you can't predict if the buffer behaves one way. You can't predict how the protein will behave in that buffer just based on the buffer data alone, as we show here. You'll need to measure it with the proteins inside. That makes sense. The proteins are the ones that are changing with their environment and reacting to the shear stresses we apply to our fluids. But here, just showing you can use activation energy to rank your different protein formulations and see which ones are most ideal to whatever application that you are working with. So again, more bovine gamma globulin data. You can see how the viscosity changes with different protein excipients, and you can look at how it changes with the Hoffmeister series. You can see how your proteins behave when you're at salting out concentrations versus salting in concentrations. Initially, we see a decrease in viscosity as the concentration of salt increases, so the proteins are more soluble. However, eventually you get to a critical point where increasing the salinity of the solution actually makes the viscosity higher than with no salt added, and thus it basically forms clusters of your different proteins in solution, causes them to interact more strongly, can lead to changes in aging and what have you. So if you recall back to the excess sodium chloride and PPS formulation from the aging study a few slides ago, that's where we were seeing here the increase in salinity, increased the viscosity, and also made it more prone to age-related viscosity changes. So this is kind of an experiment you can do to figure out what's the optimal amount of salt you can add to your formulation before it begins to hurt you in your formulation development. As we like to say here, viscosity measurements are an iterative process. You change your formulation, you probe, you see how this response, how your fluid responds to this change, and does that improve your formulation, or does it change your formulation in a way you didn't expect or don't want? And then you can go back and change again and again. And with the capabilities of the Initium 1 Plus, you can test dozens of formulations at once and figure out which formulation is right for you. And so this is one of my favorite topics in viscosity, broad range shear rate sweeps. So I'm an engineer by training, and so before joining Rio, since my knowledge of viscosity was very limited, it was basically, this is a constant in the Navier-Stokes equations. And you know, Newtonian fluids are easy and non-Newtonian fluids are hard. And that's basically the extent of what I learned in undergraduate. However, it's actually pretty interesting. Non-Newtonian fluids aren't as scary as they are made out to be. For instance, just about every colloidal suspension or protein formulation is a non-Newtonian fluid. You just have to shear it at a high enough rate before you begin to notice. So I'll walk you through this. So what this here, for the viscosity is independent of the shear rate, is called the Newtonian plateau, or where a fluid behaves like a Newtonian fluid. So at these low shear rates, this formulation is a Newtonian fluid. So this is like about 500 reciprocal seconds, all the way to maybe like 4,000 reciprocal seconds. It's a Newtonian fluid. So that means its shear rate doesn't change the viscosity. However, after this 4,000 reciprocal seconds, then now the viscosity decreases as the shear rate increases, which is called shear thinning, which is a non-Newtonian behavior. So this fluid, which is Newtonian at low shear rates, behaves non-Newtonian at high shear rates, which I think is pretty cool. And it's also pretty useful when you're doing your analysis, because sometimes maybe you want your fluid to be shear thinning. You can imagine a situation where it's fairly viscous at a low shear rate, but you want to process this fluid quickly, and you're like, man, it's so much energy to get this to flow when it's 55 centipoise. But if you can somehow shear it at 100,000 reciprocal seconds, or 10,000, this is about, I guess, 35,000 reciprocal seconds. If we can shear it at 35,000 reciprocal seconds, it's now 44 centipoise as opposed to 53, 54 centipoise. That might be enough to make it worth your while to use this formulation for processing. And then we can look at this this formulation here with 1,200 millimolar sodium sulfate, and now it's much higher viscosity, 250 centipoise, but then it dramatically shear thins at almost 10,000 reciprocal seconds, where it's now in the 165 centipoise range. And we can then fit these data to a couple models. There's the cross model, which is this dashed line here, or the Karo-Yasuda model, which is the solid line in both of these formulations. We can use these parameters that are extracted from the model to again rank our formulations. So we have this lambda parameter here, and what we can say about lambda is that an increase in this lambda is an increase in the polydispersity of our proteins in solution, which is consistent with cluster formulation. So what I mean by cluster formation is that the proteins, it's so salty, the proteins want to congregate together to avoid this excess salt. And this creates big particles, bigger particles in solution, so that it increases the effective size of the proteins in solution. And then it's also polydispersed. Since this is an electrostatic process in nature, there's going to be a broad range of different clusters that form in this formulation in particular, as opposed to this low ionic strength sodium sulfate solution. They're not going to be forming as big and varied clusters as, say, this more salty solution. Then here we can look at the concentration dependence of the viscosity behavior. So we can go from 0 concentration to 25 mg per mil all the way up to 250 mg per mil, and see how does the viscosity change as a function of concentration. And we can use that to figure out what we call the intrinsic viscosity of the protein in questions, which is basically, if there was just one protein in solution, how much would it change the viscosity? It's the infinite dilution limit of the viscosity. So how does the particle itself change the viscosity of the formulation? And and you can kind of correlate this to a size, similar to scattering techniques like dynamic light scattering. And you can also use this to rank your formulations too, because each formulation can change how the protein behaves in solution. So another key application that you can extract out of your viscosity measurements is the estimation of the injection force to inject your product into a patient. All you would need to know is the viscosity of your fluid, the shear rate that it's going to experience when you're injecting it, as well as the geometry of your needle in question. So you want the piston radius, the needle radius, and the length of the needle, and then the flow rate / shear rate of the application. And so we have a bunch of math here, which I won't go into the nitty-gritty details in, but we have several application notes and other webinars where we actually go through step-by-step the math involved in estimating the injection force. So all what we're really going to focus on is this equation here, the viscous contribution of the injection force, which is 8 times the viscosity times the needle length times the flow rate times the piston radius squared divided by the needle radius to the 4th. And this will give you a rough estimate of your injection force of a Newtonian fluid. So looking at this calculation and looking at how the force changes as a function of viscosity, you can see at different flow rates, so 0.2 milliliters per second, 0.1 milliliters per second, 0.0625 milliliters per second, you can see that it changes pretty dramatically based on both viscosity and by flow rate, and this is with a 27 gauge needle. And so we can use this to kind of predict how it's going to behave, how our formulation behaves with different viscosities and different flow rates. And here we can see again, this time based on needle gauge. So a 27 gauge needle has a narrower needle inner diameter, so it's going to have a higher force than the 23 gauge needle, which has a wider inner diameter. So it doesn't generate as much force as the 27 gauge needle. And so we can also look at how different excipients change the injection force. So typically the viscosity threshold for a product is between 20 and 10 centipoise, and different amino acids can actually reduce the viscosity such that something that's out of tolerance, out of this 50 centipoise limit, will actually fall between 20 and 50. So like 250 millimolar histidine hydrogen chloride will reduce the viscosity from about 56 centipoise all the way down to 42. And then arginine HCl, which is another amino acid excipient, can reduce it from 56 all the way down to 35. And this also dramatically changes the injection force. So PBS alone, it's 50 newtons, and then this histidine HCl 37, arginine HCl 31, and these are the assumptions we made to for these particular calculations for injection force. So just to remind you, injection force is dependent completely on the piston radius, the radius of the needle, the length of the needle, and then the flow rate that you choose. So it can change widely based on that. And then as you can see here, like we get a diminishing returns as well with our different excipients. Too much, and it begins to increase the viscosity, similarly to the salts in the earlier slides. And so Again, I like to think about aging, how the proteins change with age. Aging also impacts the injection force of your solutions. So this is the same data from before, where we have day 1 and day 92. You can look at similar shear rates. There's dramatic differences in the viscosity, which is reflected in the injection force. So at day 1, the shear rates highlighted by the red circles are 3,500 reciprocal seconds and 25,000 reciprocal seconds. And these are the flow rates that those correspond to at day 1. And we can see the injection force here is about 2 newtons, and here is about 13 newtons. Now at day 92, again, now at this point, that corresponds to 2.3 newtons, and this corresponds to about 15 newtons. So it changed subtly after 92 days. However, with this formulation, which was actually the sodium chloride, excess sodium chloride formulation, you can see a dramatic difference. So it starts at a higher viscosity, 60 versus 35, 36. Starts at 60 centipoise. And the injection force down here at 2,500 reciprocal seconds is about 2.25 newtons. But here at 26,000 reciprocal seconds, the injection force is 20 newtons. But then if we look at day 55, where the viscosity now is 76, below shear plateau, the injection force is 2.8 newtons, and down here it's 24.7 newtons. So, and that's assuming this geometry. If we change the geometry, we can make it much higher or much lower. But there's trade-offs associated with that. So, in conclusion, viscosity is more than just a single number under one set of conditions. It is a powerful tool when you fully utilize it. To select the appropriate conditions, you can correlate that to performance as a predictive tool for both your injectability and your processing and manufacturability. You can probe the interactions and microstructures of your formulations and use it as an investigative tool to guide your formulation development, because different excipients and proteins and polymers and what have you can form complex microstructure based on subtle changes in the formulation. And then you can use it to gauge your protein stability and denaturation when under storage conditions or when it's being stressed in a high temperature environment. And so I would like to thank you for your attention and interest in viscosity. I'm Zach. I'm the research scientist here, and these are people who were kind enough to put this all together. So again, thank you, and I'll be happy to answer any of your questions.
All right, so thank you everyone for listening. We'll go ahead and open the floor for any questions that you may have.
So we have a couple questions. Is this webinar recorded? Yes, this webinar is recorded, and we'll send you the recording if you've signed up for the webinar, as well as the slides. And then the next question that we have is, does the Clarity software calculate injectability by itself? And the answer is yes for the Newtonian case. So for Newtonian fluids, Clarity can calculate the injection force by itself. And it's pretty straightforward. You can change the different needle sizes, needle gauges, barrel radius, needle length, all the different parameters, and you can see how the injection force changes with your specific fluid. And then The next question is, what is the reason for viscosity increase over time? That is a very good question. We have a webinar that we recorded last summer that went into the details of that, but I'll just briefly go over part of it. So your solutions, even when you're storing them in a refrigerator, are still influenced by thermodynamics. And so your particles in solution are undergoing this process of Brownian motion, this random diffusion within the solution. And with proteins in particular, they're somewhat attractive and interactive. And so over time, they collide with each other randomly under Brownian motion. And as time increases to infinity, eventually these proteins will then collide and stick to each other, forming large clusters within the solution. And since these large clusters form, it can result in an increase in viscosity. And the time scale with which that occurs is really long when you're using refrigeration as your storage. So that's the like 30,000 foot overview of why viscosity increases over time. But if you either go to our YouTube channel or you can even download that webinar from our website, you can see that webinar from last year. I believe it's, bear with me for a second. I can look and see on our internal calendar when that webinar took place. I believe it was our August webinar. So yeah, our August webinar from last year, August 26, 2020, protein aging and solution. And you can find that on our website. So it's the full title is Solution Shelf Life Using Viscosity to Investigate Aging Protein Formulations. So, and then, all right, so the next question. So for the experiments where you measured the viscosity from high to low shear rates, did you have to use different chips or just one chip? We had to use two chips. So we used the B05 chip and the E02 chip to reach that entire range. So we basically ran the protein formulation on the B chip, and then once that experiment was done, replaced the B chip with an E chip in the initium, and then ran that same protein sample again. So, and then, yeah, so that's how you get the broadest range from, I guess it was about 1,000 reciprocal seconds all the way up to about 50,000 reciprocal seconds. And to get that range, you have to use two chips. And then what is the best cleaning protocol for cleaning out the chip? That's an excellent question. On the initium, I guess it really depends on your protein. So what we would say is to whatever buffer that the protein or formulation is suspended in, use that base buffer as the primary cleaning solvent. And then we have aquat, and then I believe acetone as the last one on the initium. You can do some, I would say, clever tricks like using a mild, like 100 millimolar sodium hydroxide solution to flush the chip once a week. Again, emphasis on mild, too concentrated on the sodium hydroxide and you can damage the chip. I also recommend doing a enzymatic cleaning step once a week, maybe at the end of the week, like on Friday before you go home for the weekend. There's a couple enzymatic cleaners out there. There's Tergazyme, and then there's also one that we've started to use more frequently called Zymet Pro. Those both seem to clean the chips out very well. So yeah, those are a couple tips So for the evaluation of temperature, is the Arrhenius equation the most used, or are other models considered? The model I've used the most is the Arrhenius equation. I'm not sure if there are other, I'm sure there are other models, but I personally haven't used them. Let's see. Next question. So question, can the initium run independently? No hands-on. Can I walk away after a run has started? Yeah, the initium can run independently. Basically, all the manpower you have to use at the beginning is to prep the samples yourself, place them on the sample tray, and then pick the correct loading, measurement, and cleaning protocols. And then once you hit go, yeah, you can turn around, walk away. You don't have to babysit it. Yeah, so it's pretty independent. And then another question, what are the practical applications to characterizing non-Newtonian behavior? Are there advantages to the initium over rotating instruments in this regard? So the practical applications of characterizing non-Newtonian behavior are pretty simple. If your fluid that you're using is going to be experiencing shear rates where it's going to behave non-Newtonian, then you'll want to know how it behaves in those situations. Let's just say you have that injection force hard tolerance, can't go past 50 centipoise, and you have a formulation that's 50 centipoise at low shear rates, but then at the shear rate that it's going to be injected, it's much higher or much lower. The viscosity is, say, 40, then it passes your criteria, so that's good. So that would be something unknown if you don't have if that'd be something good to know and allow you to use a formulation that may have been rejected, but you can say, quote unquote, save that formulation if you find that under its applications it's going to be beneath your viscosity cutoff. And then as for advantages, I guess the key advantage of our instrumentation over other forms of instruments that measure viscosity is that where we measure viscosity, there's no interface, there's no air-water interface. So there's always this issue where proteins can migrate to the interface, at least the hydrophobic parts of the proteins can migrate to the interface and then begin to unfold and aggregate, which can lead to really strange data in viscosity. And with the rotational system specifically, there is always an interface, an air-water interface, since they're exposed to the environment. So I guess our chief advantage is no air-water interface. We don't have to worry about protein denaturation, and we also don't have to worry about evaporation. So I think those are the key advantages. So what do you consider an acceptable R-squared value when evaluating the data? Is there a criteria for excluding data? Yeah, there's the short answer is, I guess the minimum that I will accept for an R-squared on the initium, and the key is on the initium, is 0.996. The other instruments like VROC microvis, you can go like 0.98, but on the initium, 0.996 is the minimum R-squared value for me. Are there other criteria for excluding data? Clarity has these built-in data quality sensors, or I guess algorithms that it looks into, and basically, if there's a bubble, it can reject the data. If the R-squareds are good, but the the transient curve of the viscosity as a function of time looks off, like it doesn't plateau, it keeps rising, or it starts to drop. Clarity has built-in logic to exclude that data. So there are some criteria built into Clarity for excluding data. So that was the last question. So I'll give you another moment and see if there's more. Yeah, okay. What are some considerations for sample prep to ensure you get good quality results? Excellent question. So a couple things that I would recommend are to use compressed air, like from a computer duster, to blow fibers out of the vials and also the caps. I would use a positive displacement pipette to load the sample into the vial. And then I would briefly, like 1 second, 2 seconds, centrifuge the vials so that there's sometimes an air bubble that forms at the bottom of the vial. So if you centrifuge it briefly, you can push that air bubble out of the bottom of the vial. So then you have all your liquid filled throughout the entirety of the vial. So then when the auto sampler enters the vial, it doesn't pick up air too. So those are like the key parts of sample prep that can help ensure good results. I guess a follow-up question, are custom vials required? No, we use Waters vials, the same vials that you use for your high-performance liquid chromatography. So it's compatible with your already existing consumables for your different instruments. Yeah, but I think we're coming up at the end of time. So I would again like to thank you for your attention and time, and happy testing.
And we'll make sure to convert the recording for everyone, and all attendees will be able to access the recording to the webinar. If you have any questions at any time, please don't hesitate to contact us. All of our contact info is on the screen that you can see here. Or if you want, just simply, you can send an email to info@riosense.com, and we'll definitely be very happy to get back to you. Thank you. Have a great evening.